So when we talk about functions, one of the things that we want to talk about is identifying and representing functions. And we want to talk about functions as an input happening and producing some kind of output via a rule, something that's happening to said input. So let's use this example. Carlos needs to buy some new pencils from the school supply store at his school. Carlos asks his classmates if they know how much pencils cost. Angela says that she buys 2 pencils for 50 cents. Paige bought 3 pencils for 75 cents. And Spencer bought 4 pencils for $1. So that leaves us asking, what is the rule that is happening here? So for every X amount of pencils, what happens that gives us this function? And you might be able to notice right away that if something is 50 cents and you bought 2 of them, that's 25 cents a piece. But if you can't recognize that, we want to look at what is happening at each of our changes in our outputs and each of our changes in our inputs. So every time that we have an increase here, we are increasing by 0.25 or 25 cents. And every time that we are increasing here, we increase by 1. So we want to make this a 25 over 1, as in our change in y over our change in x. And this is going to be just 25 cents because anything divided by 1 is itself. So we are going to have our times 0.25. So every single time that we have something, we are going to times it by 0.25. So we might say that it is 0.25x, where 2, 3, and 4 would be x. So let's say he wanted to buy 12 pencils. We would say 25 times 12, and we would get $3. Okay, so when the number of pencils is increased by 1, the cost of the pencils is increased by 25 cents. So pencils must each cost 25 cents. Since the pencils cost 25 cents, any number of pencils is a multiple of 25. This means that you have to use multiplication to find your total cost after you have decided how much each pencil costs. Okay, so one of the things that we look for in our function definition, in which a function assigns exactly one output to each input, the value that's put in is our function, and the value that we get out is our output. So this is like our x, and this is like our y, and the arrows here are kind of like our rules. And we don't necessarily need to know the rule that's happening here, because when we're looking at this, we are looking at a mapping diagram that can be used to represent a relationship between input and output values. A mapping diagram represents a function if each input is paired with only one output. So input, one output, input, one output, input, one output. So this is in fact a function. Now, since each input is paired with only one output value, the relationship is a function. And we can look here and see, well, there's 2 things coming from this. And since 2 is paired with more than one output value, both 4 and 5, the relationship is not a function. If there are 2 arrows coming from our input, this cannot be a function. Oppositely, if we have more than one output value but only one, if we have more than one input value but only one output value, this is still only one arrow coming out of each input. So this is in fact a function. And this is another example of that. 7 is going to one thing, 8 is going to one thing, and 9 is going to one thing. Even though 8 and 9 are going to the same thing, they're each only given one output. So that is in fact a function. Another way that we can see this is in tables, where we're looking at x as our input and y as our output. So let's say that we have this input 5, 10, 15, and 20, and our output 7, 6, 15, and 2. Here, since each input value is paired with only one output value, the relationship is in fact a function. Now let's imagine for a moment that we had, say, 25 and 15. Would that still be a function? Since 15 is a repeated output, one output value is paired with two inputs. If this occurs in a relationship, the relationship can still be a function because 15 is paired with 15, 25 is paired with 15. So we're only looking at a repeat of x's. So this is a function even with this 25 to 15. We're looking at a repeat of x values. If they're repeats in x, then it cannot be a function. So let's look here. 1, 5, 4, 1. Here's a 1 and here's a 1 and 7. Now let's say that if we had 1 and 10 and 1 and 10, then this would be a perfectly fine function because it's the same point. But this is 1 and 10 and 1 to 4. So 1 is being paired with 10 and 1 is being paired to 4. This is not a function. So let's move down here. So we want to see, is this a function? Each input value is paired with only one output. So even though they're the same number input to output, 53 is only paired with 53, nothing else. 24 is only paired with 24, 32 is only paired with 32, and so on. So this is, in fact, a function. Okay, so now we're going to look at dot graphs, and I have written the dot graph and plotted the points so that we can see exactly what's going on. Now, if we look at this, we can see that there are two things happening on the same x-axis. If this is our x and this is our y, then we can see that two things are happening at this x, and there's also two things happening at this x. And this is a little hint as to how graphs work and how plot points work. So if we look at all of our plot points, we can see here that here is a 2 as an x and another 2 as an x. Here's a 9 as an x and another 9 as an x. And we want no repeating x's in order to have a function. So this whole graph, this whole situation is not a function because we have two repeating x's in two different places. Now if we got rid of one of these points in each space, then we'd have one value at 2 and one value at 9, and then we'd have a function. Okay, so here we don't have anything that looks like it's crossing over each other, so we're going to look at our x values just to make sure. 1, 1.5, 2, 3, 4, and 5, and this is a function. There are no repeating x's, there are no things that are going all the way straight down. So that is an example of how that works in a graph situation. Now, once we have discovered what a function is, we need to learn how to describe functions. The U.S. Department of Agriculture defines heavy rain as rain that falls at a rate of 1.5 centimeters an hour. So we're going to decide if this is how much time it has been, and this is the rainfall, and we need 1.5 centimeters per hour. We want to find out what happens at 2 hours, 3 hours, 4 hours, and 5 hours. So we know that per hour means that we're multiplying by the hour, and we know that it's 1.5. So our 2 would have to be 3, 3 would be 4.5, 4 would be 6, and 5 would be 7.5. Okay, and that is a function, and this is actually going to be a linear function where it is going to give us some straight line. And what we want to notice is that all the points fall on this line. If we had 0, 0, 1, 1.5, 2, 3, 5, 4, 3, 4.5. And we also want to notice that if we happen to find 1.2, 2.5, 3.6, we'd end up getting more and more points in between these pieces. So we could actually draw a line straight through and have a connecting dot at each individual point. Okay, and that is where we're going to head with linear functions. So now we're going to look at another example. The temperature at dawn was 8 degrees Fahrenheit, so immediately our temperature was 8 degrees Fahrenheit. and it increased steadily 2 degrees Fahrenheit every hour. So 2 degrees every hour. It's 2 every. So that means that that is what we are multiplying by. So we are going to take this rule. We are going to say 2 times 0 plus 8, and that is 8. We're going to say 2 times 2 plus 8, that is 4 plus 8 is 12. We're going to say 2 times 4 plus 8, that is 8 plus 8 is 16. We're going to say 2 times 6 plus 8, that is 12 plus 8 is 20. So now we are going to fill in our x, y's, which we are just going to take our x and our y, 0, 8, 2, 12, 4, 16, and 6, 20. Now, we are going to talk briefly about if these are proportional or non-proportional, because they are functions, they don't have any repeating x's, and they are linear, which means they're going to form a line. Typically, if you have something that is a function, it is going to be some sort of line. It is really up to the rule that you use depends on if it is going to be a straight line, if it is going to be some kind of curve, some kind of parabola, and we will talk about some examples of that later. Proportional or non-proportional. Proportional means that we start at the origin, or we have something that looks like y equals mx without the b. So we either started at the origin, which is 0, 0, or we have no plus here. So our first example, we actually have a 0, 0, so this is proportional. Okay, but here we actually can see that we have a plus b, and when we started at 0, we were at 8, so it is not proportional. Okay? We are going to do some more describing functions. We are going to look at 5 minus 2x. We are going to plug in -1, 1, 3, and 5. Now, if we plug in 1, we're going to get -1, we're going to get 2 times -1 is positive 2, plus 5 is 7. If we plug in 1, we're going to get 1 times 2 is 2, 5 minus 2 is 3. If we plug in 3, we're going to get 2 times 3 is 6, 5 minus 6 is -1. And then if we plug in 5, we're going to get 5 minus 2 times 5 is 10, 5 minus 10 is -5. And so if we graph that, we're going to start here, -1, and go up to 7. We're going to go to 1 and get 3. We're going to go to 3 and get -1, and then we're going to go to 5 and get -5. And I'm just doing a rough draft so we can see exactly what's going on here. Okay, so this is a linear, okay, but we are not going through our origin. So this is a linear line, but it is non-proportional. Okay, so these are the two things that we're really hitting on, linear and proportional or non-proportional. So we're talking about linear or non-linear, proportional or non-proportional. If it is proportional, it is automatically linear. Okay, so linear has the opportunity of being proportional, but if we saw immediately that it was proportional, it's going to be a linear graph. Okay, so we're going to look at the next thing, which is 2 minus x squared. We're going to look at -2, -1, 0, 1, and 2. Okay, so if we plug in -2, we're going to get -2 squared is 4. 2 minus 4 is -2. If we plug in 1, we're going to get -1 squared is 1. 2 minus 1 is 1. If we plug in 0, all of this is going to go away. We're going to get a 2. 1 squared is 1. 2 minus 1 is 1. 2 squared is 4. 2 minus 4 is -2. Okay, and then we're going to graph this. At -2, we're going to be at -2. At -1, we're going to be at 1. At 0, we're going to be at 2. At 1, we're going to be, I'm sorry, this is up here. We're going to be at 1, and at 2, we're going to be at -2. So we're going to draw this, and the more practice you get, the more you'll see that if you have an x squared, you are going to have a parabola shape, and because it is negative, it is going to be facing down. So we can immediately say this is nonlinear, this is not a line, and because it is nonlinear, it is non-proportional. If you do not have a linear situation, you cannot have a proportional situation, because proportional means that we're going up or down at a steady rate, and this is doing an up and down motion, and so that cannot be proportional. Okay, so we are going to go ahead and start looking at comparing functions. So when we compare two functions, we are going to be looking at the differences mainly in their slope, and we're going to see exactly, sorry, that should be a 10. We're going to see exactly what is happening at a certain point given the situation. So Josh and Maggie buy MP3 files from different music services. The monthly cost $Y for X songs is linear. The cost of Josh's service is Y equals 0.50x plus 10. And the cost of Maggie's service is 0.99x. So, then we want to know which service is cheaper when 30 songs are being downloaded. So, even though there's something happening that's different than what's happening over here, we can still plug in X and find out exactly what is happening. So 50 times 30 we wanted to know, plus 10, and 99 times 30. Okay, so we are going to find out that 50 times 30 is 15. We're going to add 10, and that is 25. And then we are going to do 0.99 times 30 and end up getting 29.7. So Josh's service, this is Josh and this is Maggie, Josh's service is actually cheaper than Maggie's service of $29.07 versus $25. And a lot of times when we see comparing functions, we'll compare between a graph and a table. So if we wanted to see an example of, let's say, 6.95x plus 1.50 versus a table, which is 7.5 to 15, we could find what happens. We could find what happens at the slope, which is going to help us drastically in determining what is going to be cheaper. So let's say this is the cost of buying books at a bookstore, and this would be buying books online. So we're going to find the difference that is happening here, and it looks like this is 7.5 x plus, if you didn't buy any books, there'd be nothing to do. So we're going to take a look at what's going to happen. Let's say if we buy 2 books, which we already know that that's 15. If we buy 2 books here, we are going to have a little bit of math to do. 13 plus 150. Okay, so it's actually cheaper to go to this bookstore and buy the books than it is to have an online service. And what you can see, if you just were to look at the y-intercept, if you were to not buy any books at all, for whatever reason, you would get 0. But if you were to buy no books at all here, for whatever reason, you'd spend 150. And this is where things get a little complicated in understanding real world situations. But this is a proportional relationship, and this is non-proportional, which almost automatically makes this a more expensive option, because even if you buy nothing, you are spending money, which obviously doesn't make sense in a real world situation. However, in the linear graph that we have here, this is what happens. Maybe you buy online and this is what it costs for shipping. And let's just say that you bought something, not a book, and still paid for shipping for pencils or something like that. You'd pay that $150. So then we're going to talk about analyzing graphs. Analyzing graphs is our final step in talking about functions. We just need to understand what is happening in our graph. So when we have a slope that is going up, we read graphs from left to right. When we have a slope that's going up, this is a positive slope. That means you are gaining speed, you are gaining money, you are traveling away from your home, you are doing something in a positive manner compared to the two variables that are happening here. Now, if you have both of these things side by side, you may say that you are going quickly or slowly positive. You're going quicker or slower up. You're gaining speed faster. You're gaining speed slower. You are going farther away from home quicker. And if you have them individually, you may just say that you are increasing and increasing. You may not necessarily point out that you are going quickly or slowly because it's more of a comparative option. But let's say you have them right next to each other. You can say that this is rapid. You are going quickly here, and you are going slowly here. You are going from 0 to 40 miles an hour in a short time. Maybe you are gaining speed to get onto the main road, and then you are going slowly up. Maybe you're merging onto the highway, so you're going from 40 to 60, or something similar to that. The opposite, of course, if you are going down, we're going left to right. If you are decreasing, you have a negative slope. This would be maybe slowing down for a stop sign, maybe losing money on an investment, and of course you could say that you are losing money quickly, or losing speed quickly or slowly. And again, you may not see it as quick or slow if they're individual and by themselves, but if they're right next to each other, you may be able to say that this is more slow and this is more quick. So you could say that you are slowing down in the traffic, or maybe as you're getting onto the main road, and then you are slowing down quickly for a red light at the intersection. And then another situation that happens in a graph is if you are going a constant speed. This is you're on the highway and you are constantly going 60 miles an hour, or you had a break in spending money and had a break in getting money, so you're at this constant rate of however much money in your bank account. And so this is constant. And so we don't want to say that these are constantly going down. We want to say that these are continuously or steadily going down or going up. We want to say that this is a constant rate. And so then we can look at a combined graph together where you can say that something like segment 1 shows the attendance during the opening weeks of a park season. So there's a steep upward slope that shows the attendance rising quickly in segment 2, while there was just a steady stream of people coming in at segment 1, the increase, we could say maybe from summer break with school, maybe it's getting hotter so people want to be indoors more. You can say that segments 4 and 5 are decreasing. The decrease might coincide with summer break ending and when school starts again, so you may have less people showing up, less students, less children, less parents, because they have to bring their kids back to work. They don't have their kids to take with them. The positive slope shows an attendance increase, while the negative slope shows an attendance decrease. And so we have these time of months. Maybe this is January, February, March, April, May, June, July, August, September, October, November, December. And we have this amount of visitors that's happening. Maybe this is 20, 30, 40, 50. And we're reaching this max, and then we're going back down. So we just want to be able to understand what is happening at the given situation, and maybe we take away visitors in months, and maybe we talk about speed in our car. Maybe we're driving on the highway, maybe we're driving in a residential area, increasing speed slowly to get on the main road, increasing again because we got on the highway, getting off the highway, and stopping at our destination. There are a lot of different ways that we can interpret this graph, especially if there are not labels. If we just had a graph, we could make up any situation that makes sense, but because of the time and the visitors and understanding that this is maybe a roller coaster park or maybe a seasonal show, we can see exactly what's happening and we can give it a reasonable description. So, we have learned a lot about functions. We have learned what a function is, talking about a repeating of x's is not a function. And this includes This includes things like repeating of inputs, repeating of x values. We have talked about comparing functions between each other. We've talked about comparing the slope and plugging in an x value. We have talked about proportional versus non-proportional, and we have talked about linear versus non-linear, and we have talked about coming up with a situation to a graph, which we usually call analyzing that graph.